Namaste students. Let us continue with the solving of numerical problems on slot loading and design of stator, correct. So let us consider the third problem. So determine the D and L. D is the stator bore diameter and L is the core length of a 70 HP 415 volt 3 phase 50 hertz star connected 6 pole induction motor for which AC is a specific electrical loading which is 30,000 ampere conductor per meter and specific magnetic loading 0.51 Weber per meter square. Efficiency is 90% and power factor is 0.91 and pole pitch equal to core length. Estimate the number of stator conductors required for a winding in which the conductors are connected in two parallel paths. So that means there is a two circuits or two parallel paths. Choose suitable number of conductors per slot so that the slot loading does not exceed 750 ampere conductor. So that is the statement of the problem, which is similar to that of a previous problem. Okay. So first initially we need to find out the value of kVA input. So kVA input Q is equal to HP, the value which is given in HP. HP into 0.746 you will be getting in terms of kilowatt, correct. Kilowatt if you divided by power factor, so you will be getting kVA, and if you multiply with the efficiency you will be getting the kVA input. So HP it is given in the problem, statement of the problem, the values are given in HP, and if you multiply with the 0.746 that you will be getting in terms of kilowatt, the value you will be getting in terms of kilowatt. If you divide by power factor the value will be giving in terms of kVA output, correct, output in kVA, into efficiency is 0.91, so you will be getting kVA input. So the value you will be getting 63.76 kVA. So output coefficient C naught equal to 11 into BAV into AC into KWS. S is a stator, that is winding factor, stator winding factor, into 10 to the power minus 3. So 11 into BAV is 0.51 it is given, into 30,000 AC into KWS is stator winding factor, that is 0.955 into 10 to the power minus 3. So you will be getting 160.72 kVA per meter cube in RPS, correct. So synchronous speed NS is given by 2F divided by P. So 2 into 50 divided by number of poles is given as 6. So it is 16.66 RPS. So the value of synchronous speed is NS is represented in RPS. So we have D square L. D square L is given by Q divided by C naught into NS. Q is the output in kVA divided by C naught. C naught is the output coefficient into synchronous speed, that is NS. The value of Q what you are got is 63.76 divided by 160.72, that is the C naught, and into 16.66 is the NS. So you will be getting D square L value is 0.0238 meter cube. So it is given that tau is equal to L, that is pole pitch is equal to core length, that is L. So but tau is nothing but pi d divided by P, correct. So from this L is equal to pi d divided by P is 6, which is equal to 0.5236 D, capital D, correct. So capital D you are substituting here in this value. So L value will be equal to 0.5236 into capital D, so pi by 6. So putting L in equation 1 and simplifying, D is equal to, you will be getting 0.35688 meter and L is equal to 0.19 meter. So that is the value of D and L when you are substituting in the equation number 1. So you will be getting the core length and the stator bore diameter values. Flux per pole phi m you can get it from BAV into pi dl divided by P. So we have specific magnetic loading BAV equal to, so this is the equation. From that equation you can calculate the flux per pole, that is BAV, that is 0.51 into pi into D what you are getting, it is round up as 0.36 and L value is 0.19 divided by 6, that is the number of poles, that is 0.0183 Weber. So turns per phase TS is equal to ES divided by 4.44 F into phi m into KWS. So since it is called as a star connected star connected winding. So ES value is 415 divided by root 3. So you will be getting in the per phase value. So 415 is the line voltage. So 415 divided by root 3 you will be getting the phase voltage. So 4.44 F is the 50 hertz and 0.0183 is the 5M what you are getting from here, and into stator winding factor is 0.955. So solving this one you will be getting turns per phase as 62. Since the conductors are placed in two parallel paths, so in the statement of the problem it is given that conductors are placed in two parallel paths or there are two circuits. So total stator conductors equal to 6Ts into 2. So that is 12 into Ts. So 12 into 62, so that is 744 conductors are placed. So since there are two parallel paths, so you can multiply with the 2. So that is 12 Ts, that is 744 conductors. So slot pitch YSS should lies between 15 to 25 millimeter. So when YSS is at a lower value, that is 15 millimeter, so number of stator slots you can calculate it by pi d divided by YSS. So you will be getting 75 as the number of stator slots, and when YSS is equal to 25 mm, so YSS that is upper value, then the number of stator slots will be equal to 45. So the number of stator slots lie in the range of 45 to 75. So when the number of stator slots should be within the range of 45 to 75 by using these two equations. So when slots per pole per phase, that is Q is equal to 2, then number of stator slots equal to 36, correct. That is slots per pole per phase, 3 into 6 into 2. That is 36. When slots per pole per phase is 3, that is SS is equal to 3 into 6 into 3, that is 54. When slots per pole per phase is 4, then number of stator slots equal to 72. So by using these these three values, number of stator slots will be lying between 45 to 75. So that means you can have these two number of stator slots when the slots per pole per phase is 3 and 4, correct. So the value of stator slots lies between 45 to 75 are stator slots is equal to 54 and 72, correct. Stator current per phase IS is equal to kVA into 1000 divided by root 3 into VL. So kVA is 63.76 into 1000, that is divided by root 3 into line voltage is 415 volt. So you can calculate the stator current per phase, that is 88.75. So since it is a star connected, so phase current and line currents are same. So whatever the value you are getting here as a line current, actually that is IL. So since it is same, so stator current per phase IS is equal to 88.7 amps. Current through the conductor IZ is equal to IS divided by A. A is the number of parallel paths. Since it is a two parallel path it is given, so we need to divide it by 2. So if it is only one parallel path, so the value of IS should be equal to IZ. So IZ is now it becomes 44.35 amps. Now check for the slot loading. When the stator slots equal to 54, the conductors per slot is given by ZSS equal to 744 is the total number of conductors divided by stator slots, that is 54. So there will be, you will be getting the conductors per slot is 14. So slot loading is ZSS into IZ. So 14 into 44.35. So you will be getting 620.9 ampere conductors slot loading when the stator slots equal to 54. When the stator slots equal to 72, then conductors per slot is ZSS is equal to 744 divided by 72. So you will be getting 11. So slot loading is ZSS into IZ equal to 11 into 44.35. So you will be getting 487.85 ampere conductors. So in the question the slot loading is given as 700 ampere conductor. So both in both the cases slot loading is not exceeding the given value. So in that case we need to choose the less number of stator slots. So there will be a choice of choosing the stator slots between 54 and 72. So in that case normally we need to choose the less number of stator slots, that is SS is equal to 54. In that case the total stator conductors equal to ZSS into SS. So you will be getting 14 into 54. 14 is the total number of conductors per slot, and into 54 is the number of stator slots. So, you will be getting 756 conductors. New value of turns per phase Ts is equal to ZSS into SS divided by 6 into 2. 6 into 2 is total number of 6 Ts, correct. So, total is 6 Ts and 2 parallel paths. So, you need to multiply by 6 into 2. So, there will be 63 is the new value of turns per phase after checking the slot loading. So, that is how you need to solve this these kind of problems with the stator slots. So, here we need to designing the, or we have already designed the stator slots, correct. Now, next part of designing of induction motor is the length of air gap. So, between stator and rotor slots there will be a small air gap is there. So, what is the length of air gap and what is the value to be chosen for the length of air gap that we need to find out. So, length of air gap, the symbol for that one is L suffix G, length of air gap. So, if you see the induction motor here, so here the outermost part is the stator part. So, these are all the stator slots you can see. So, this is a stator or yoke part, that is blue color part is a stator or yoke, and these are all the stator teeth, correct, stator teeth. So, or you can say that stator slots or slot winding which is present inside the stator slots, and these are all the rotor slots which are present inside. These are all the rotor slots, correct. So, in between the yellow line, a thin yellow line which is shown, so that is the air gap between the stator slots and the rotor slots, a small air gap is present. So, this is a rotor part, correct. So, we need to find out we need to design the length of air gap for an induction motor. So, length of air gap will be of an induction motor is decided by considering the following factors. So, when you are choosing the length of air gap of an induction motor, we need to consider the following points. Based on the following points, we need to choose the length of an air gap of an induction motor. So, first one is the power factor. So, we need to consider the power factor of an induction motor. Based on the power factor of an induction motor, because the power factor of induction motor is very important thing. Normally, the power factor of induction motor is normally it is less when compared to transformer and all. So, that is the one of the deciding factor for choosing the length of an air gap. Second point is the overload capacity. How much is the induction motor is taking the overload capacity. So, that is also one of the factor to be considered for the choosing of length of air gap of an induction motor. And third point is pulsation loss. When the induction motor is rotating with high speed, so there will be a pulsation loss will be taking place of the rotor slots and stator slots. So, when it is continuously running with high speed, so there will be pulsation losses will be taking place in the induction motor. And fourth point is the unbalanced magnetic pull. So, unbalanced magnetic pull is the irregularity in the stator and rotor. So, stator is not centrally concentrated on the, rotor is not centrally concentrated on the stator. So, there will be uneven distribution of rotors in the stator, correct, inside the stator. So, there will be a change in the length of air gap will be taking place. So, that we have to consider. And next one is the cooling, how the cooling of induction motor will be taking place. So, what type of cooling you are providing for the induction motor. So, based on that one you need to choose the length of air gap. And the next point is the noise. So, to reduce the noise, what is the length of air gap you have to choose, or if it is the noise is higher, what is the design parameter to be considered for the reducing the length of air gap, that we have to consider. So, first part is the power factor. So, we need to improve the power factor of an induction motor, or we need to consider the power factor of an induction motor. The MMF required to send the flux through the air gap is proportional to the product of flux density and the length of air gap. So, whatever the magnetic motive force which is present in the air gap, or what is the magnetic motive force which is required to send the flux or distribute the flux in the air gap to in the air gap. So that will be proportional, that is not equal, it is proportional to the product of flux density, what is the amount of flux density, that flux per unit area, and the length of air gap. So here area is nothing but the length of air gap only. So it is flux density means flux per unit area, correct. So flux per unit area into multiply with the area of the flux which is traveling inside the air gap, correct. So that will be equal to the total flux. So you can say that the magnetic motive force which is required to send the, or you can or it should be distributing the flux which is present inside the air gap is nothing but it's a proportional to the product of flux density and the length of air gap. So even with very small density, if the flux density is very small, the MMF required for air gap is much more than that for the rest of the magnetic circuit. So if the length of air gap, if it is reduced, or you can say that length of air gap if it is reduced, then the area required for the distribution of flux is reduced, correct. So there will be more flux densities takes place, more flux densities takes place, because the amount of flux will be same and the area is reduced, so the flux density will be more. Or in other words, if the flux density is very small, even with very small densities, the MMF required for air gap is much more than that of the rest of the magnetic circuit. Therefore, it is length of air gap that primarily determines the magnetizing current drawn by the machine. So whatever the magnetizing current which is drawn by the induction motor will be depends upon the length of the air gap, So we can say that if the length of air gap is higher, the power factor will be lower, correct. So next point is the overload capacity. The length of air gap affects the value of zigzag leakage reactance, which forms a larger part of total leakage reactance. What is meant by the zigzag leakage reactance? So the flux will be distributed in the air gap is like this in the zigzag fashion. So that is called as a zigzag leakage flux. So or the reactance which forms from the leakage flux is called as a zigzag leakage reactance. So this is a, we can say that this is a stator slots, stator part of an induction motor, and this is the rotor part, and this is upper one is the stator part. So in between there will be air gap which is present in the induction motor. So this is a stator part and this is a rotor part, and there will be air gap is present in the induction motor. So that is called as a length of air gap. So the flux which is distributing in the air gap is of zigzag in fashion. So you can see here, so there will be zigzag in distribution of flux. So the length of air gap affects the value of zigzag leakage reactance, so which forms a larger part of total leakage reactance. So if the length of air gap is higher, the leakage reactance, zigzag leakage reactance will be very less, or it will not be affecting the stator and rotor slots. If the length of air gap is large, then the zigzag leakage flux will be less, and so the leakage reactance will be less. So if the air gap length between the stator and rotor is higher, then there will be a less leakage reactance, or the leakage flux will be less, and that leakage flux will not be affecting the stator and rotor slots, correct. So because the air gap length is higher, if the air gap length is lesser, so the leakage reactance and the leakage flux will be more, and it will affect the stator and rotor slots, correct. With the lesser value of leakage reactance, the overload capacity of the machine is increased. If you see the characteristics curve of an induction motor, that is, you can say a circle diagram. So if there is a leakage reactance value is less, or the leakage flux value will be lesser, then the diameter of the circle diagram will be higher. So which increases the overload capacity of the induction motor. So you can say that with the lesser value of leakage reactance, the overload capacity of the induction motor will be higher, correct. So hence the greater is the length of air gap, greater is the overload capacity. So third point is the pulsation loss. With the larger length of air gap, the variation of reluctance due to the slotting is small. So reluctance which occurs due to the slotting of an induction motor. So the accommodation of slots which are, or the accommodation of conductors which are present, which are inside the slots. So or the punching of the slots in the stator or rotor. So that is called as a slotting. So with large length of air gap, the variation of reluctance value will be very small if there is a large length of air gap. The tooth pulsation loss, the tooth means slots area, slot part which is not covered with the opening of the slots, correct. So other than the opening of the slots, you can say that it is a tooth of a slot. The tooth pulsation loss which is produced due to variation in the reluctance of the air gap is reduced accordingly. So tooth pulsation loss which is produced due to variation in the reluctance. So variation in the reluctance in the air gap, there will be a tooth pulsation loss will be there. So that will be reduced if there is a length of air gap is much higher. Therefore, the pulsation loss is less with the large number of air gaps. So if the length of air gap between stator and rotor is larger, so there is a less pulsation loss, because the tooth pulsation loss will be lesser in that case. The leakage reactance or reluctance to the flux will be lesser. Next, unbalanced magnetic pull. If the length of air gap is small, then even a small deflection or eccentricity of the shaft would produce a large irregularity in the length of air gap. So this is the stator and this is the rotor part. So the stator, this is a shaft of an induction motor, which is directly considered, correct. So it is a straight, you can say straight. This is a stator part and this is a stator and this is a rotor. So this is shaft of an induction motor is placed continuously, or you can say that it is straight, uniform eccentricity, you can say. So here if you see the second figure, so there will be slightly deflection in the shaft. So slightly deflection in the shaft. So you can see here, so this is a fully oval shape and there is a deflection in the shaft, or deflection in the rotor will be, you can observe here. So or you can say there is a small deflection in the shaft is there between the stator and rotor. So you can say that it is case 2, that is eccentricity at one end, So there is a small deflection in the shaft, correct. So here it is a much deflection in the shaft, correct. Eccentricity in opposite direction at each end. So here much deflection in the shaft, you can say. So here the shaft position is slightly oriented, or it is not horizontal, correct. So if the length of air gap is small, then even a small deflection or eccentricity of the shaft would produce a large irregularity in the length of the air gap. If you design a small length of air gap, so if there is a deflection in the shaft, or which in turn deflect the rotor, correct. So a small deflection in the shaft also, or small deflection in the rotor also will change the uneven distribution of length of air gap in the correct. So that is the case. So it is responsible for production of large unbalanced magnetic pull, which has the tendency to bend the shaft still more at a place where it is already bent, resulting in fouling of rotor with the stator. So if there is a slightly deflection in the shaft, if it takes place, so there will be, when it is continuously rotating, so there will be a possible of bending of the shaft takes place at many places, correct. So that will result in the fouling of the rotor with the stator. So it is rotor and stators are not uniformly arranged, so there will be a fouling of rotor and stator will be taking place. So if the length of air gap of machine is large, a small eccentricity would not be able to produce noticeable unbalanced magnetic pull. So if the length of air gap is in the machine is large also, so a small eccentricity, a small deflection in the air gap is also, a small deflection in the shaft is also not much, it is not giving any much noticeable unbalanced magnetic pull. Next we have to see the cooling of an, what is the effect of cooling. If the length of air gap is large, the cylindrical surface of the rotor and stator are separately by a large distance, correct. So if the length of air gap is designed a large, then cylindrical surface of the rotor and stator. So if you see in the three-dimensional view, then it is a rotor and stators are in cylindrical in surface, correct. So cylindrical surface of rotor and stator are separated by a large distance. So there will be large distance between stator and rotor if the length of air gap is large. This would afford better facilities for cooling at the gap surfaces especially when the fan is fitted for circulation of air. So length of air gap is large means there will be a large distance between the stator and rotor, correct. So that will give the better cooling effect in the gap surfaces when the fan is fitted in the circulation of air. Next, noise. The principal cause of noise in the induction motor is the variation of reluctance of the path of the zigzag leakage flux. So we have already seen that there is a zigzag leakage flux will be present in the air gap of stator and rotor. So if the length of air gap is large, so the zigzag leakage reactance and zigzag leakage reluctance will be lesser. So that will avoid the noise of an induction motor, because the stator and rotor gap is large if there is a large length of air gap. So there will be a communication or the effect of rotor slots and stator slots effect will be lesser, correct, lesser if the length of air gap is higher. If they are closely associated, stator slots and rotor slots are closely arranged and the length of air gap is less, so there will be a noise production or the formation of the noise when the rotor is continuously rotated. So if the length of air gap is higher, the noise will be reduced. So to ensure that the noise produced will not be objectionable, it is necessary to make the zigzag leakage as small as possible. So zigzag leakage flux is as small as possible. So this to achieve this one, so there will be increase in the length of air gap can be done. So zigzag leakage flux will be reduces. So that can be achieved by increasing the length of air gap, correct. So summarizing all the points, we can say that length of air gap should be small for what cases, which cases, in order to keep down the magnetizing current and improve the power factor. So if I want to improve the power factor, so length of air gap should be small, and in order to keep the magnetizing current. So lesser air gap will advantage for the reducing the magnetizing current and improving the power factor. So improving the power factor is one of the prime importance in the induction motor. So length of air gap should be large to get the higher overload capacity. If the overload capacity we need to improve, or if you need to get the higher overload capacity, then the length of air gap should be larger, and better cooling. If you want to achieve the better cooling, length of air gap should be larger, and reduction in noise and reduction in unbalanced magnetic pull. So if the length of air gap is larger, we can have 4 advantages, and we will get the increased overload capacity, better cooling, reduction in noise, and reduction in unbalanced magnetic pull. And the length of air gap, if it is small, then we will achieve the good in power factor, and we can keep down the magnetizing current. So normally the length of air gap can be calculated by using this empirical formula. So Lg is equal to 0.2 plus square root of 2 into square root of dl. 2 into square root of dl in millimeter. So whatever the value you are getting, that is the value is in millimeter for small induction motor. So Lg is equal to 0.2 plus 2 into square root of dl. D is the stator bore diameter, L is the core length, correct. So Lg is equal to 0.2 plus d in millimeter for general use. General use, you can use this also. For normal induction motor, you can use the formula for calculating the length of air gap. So these two formulas are used for the length of air gap, to calculate the length of air. So we will stop here. We will continue with the next video.